Hi, I'm Yumi Choi from the Korea Research Institute of Chemical Technology. My topic is utilization of dipicolinic acid as a starting monomer of compostable polymers. If you are concerned about the environment, you're probably used to the pictures below. This is a straightforward picture showing that plastic is the main culprit of ecosystem destruction. It is expected that plastic will hurt human health through the food chain. Dipicolinic acid is from some bacterial spores. It means it can be rapidly biodegraded by pure microbial cultures. It can extract heavy metals from contaminated soil as a chelating agent. I expect rigid properties like easier stacking and crystallization from pyridine moiety and hydrogen bonding. However, even it has a rigid property, there is some difficulty in the classic esterification due to thermal decomposition into monocarboxylic form or pyridine at around 230 Celsius degrees. I already synthesized the polyol from DPA and 1,4-butanediol. But DPA is thermally unstable and easily decomposed into pyridine and carbon dioxide. So instead of thermally unstable dipicolinic acid, I used the dimethyl form of DPA. The reason why I used 1,4-butanediol is to protect the functional group of monomers by extending the aliphatic chain and to solve the thermal decomposition problem. After synthesizing with dimethyl EPA and 1,4-butanediol, I checked the structural properties through proton NMR. As you can see, most of the products are not reacted or decomposed a lot. Pyridine, which is completely decomposed, has not been found. Its peak is predicted at around 7.2 ppm. It means the only one functional group was decomposed during synthesizing. It is almost similar to FTIR results. Therefore, the esterification reaction of dimethyl EPA and 1,4-BD is not an appropriate method. On the next slide, I will show you the new method of utilizing DPA. To make an amide bond on the bifunctional group of DPA, I synthesized the DPA and ethanolamine, EDC as a carboxylic activator, triethylamine as a catalyst, and HOBT as a nucleophile were used respectively. The predicted target material has two amide bonds on the functional side, and the isourea byproduct is extremely water-soluble and can be eliminated by an aqueous workup. This synthetic process is for making a polyol of compostable polyamide urethane. As a carbon NMR result of amidation, the monomer disappeared. Some peaks of final products can be thought of as a target material. However, there are too many peaks than 8, which is estimated from the target structure. So I guess the yield of synthesizing is quite low and most of the reactions will be side reactions. Consequently, the potential of DPA as a novel bio-based monomer was investigated. Since the structural property of DPA poses a thermal decomposition problem in classic esterification, modification of DPA is vital. As seen from the above, the amidation of DPA with isocyanate can be an attractive reaction for compostable polyamide urethane rather than esterification. This is the end of my presentation. Thank you for having me.